All right, we've jumped around a little bit in this unit on bonding. We've covered the ionics, we've covered the metallics, and so the last type of bonding is covalent bonding. Covalent bonding comes between non-metal atoms. So ionics were always metal, non-metal, and obviously metallic bonding is all metals. Covalent bonding is all non-metals. And we're still trying to achieve, full stable octets, but we're just going to do so in a little bit different way, especially when we look at the nature of these atoms and how they can get that full outer shell. Now, one other thing that we should mention is that the ionics were always thought of as these big crystals where you can't really tell where one molecule starts and another one ends. I could have a crystal of sodium chloride, and it's just all of these ions that pack real tight together because the attractive forces are so strong, right? And we're talking about these really strongly charged ions, positive, negative, positive, negative, positive, negative, positive, negative, positive, negative, positive, negative. And so the ions just packed together in this very organized crystal structure. And so here you just kind of can't tell where one molecule starts and another molecule would end. Like, is this a molecule of sodium chloride? Is this a molecule of sodium chloride? I don't know. And so that's why when we write the ionic formulas, we write it as the simplest repeating pattern of the crystal. And so we write sodium chloride as NaCl. It's a 1-to-1 ratio of positive ion to negative ion. But the covalents are a little bit different. They're not going to have these strong charges that create the strong attractive forces. And instead, they're just going to exist as individual molecules. So I'm not going to have like this big crystal anymore. It's just going to be a bunch of molecules. And so maybe it's something like water. Water is going to end up being a covalent structure. And so water molecules kind of look like this. They're like little Mickey Mouse heads that are kind of upside down, where the oxygen is the big atom and the two hydrogens are the little atoms. And so water is just a bunch of these little molecules. There they are. And so it's easy to tell where one molecule starts and one molecule ends. So I can write the formula as H2O. So it's a little bit different than just the structure of an ionic compound in that there's just a whole bunch of ions that are packed real tight together in this very organized repeating crystal pattern. And it's a little bit different with covalents. It's going to be individual molecules, and obviously they can still be solids. You could have ice, and then these molecules will just pack together, but you can still distinctly tell where one molecule ends and another molecule begins. Now, in order to make these covalent molecules, we're going to overlap orbitals. So earlier in the atomic structure unit, we had talked about the s orbitals and the p orbitals and the d orbitals. And while here they go into a little bit more than what we need, in that these orbitals kind of mix together to make special hybrid bonding orbitals. Well, the hybrid orbital stuff we'll save for a second year course. In a second year chem course, we go a lot more in depth with how these orbitals mix to make special bonding orbitals. But for now, all I want you to understand is just that the orbitals overlap. And so carbon's got his orbitals, and there's the p orbitals and s orbitals, and hydrogen just has an s. It's just the 1s1 orbital, right? And so eventually we're going to share electrons instead of transferring electrons. And to share, the orbitals just have to overlap. So in this region here, where the orbitals overlap, you could have the sharing of 2 electrons. And we often show those electrons as little arrows, kind of pointing in opposite directions, showing that they spin opposite. And so you can kind of do the same thing with these little bubbly orbitals, that they just have to overlap. And in the region of overlap, we can share electrons, which is what they kind of mention here. We're still obsessed with the octet rule. We're still trying to get full, stable outer shells. That's the whole purpose of any kind of bonding. But now we're just going to do it in a little different way. We're going to share electrons instead of transfer. And so here's what happens. You get a bunch of nonmetals, and the nonmetals are this pretty small section of the periodic table, just the upper right-hand corner, starting with carbon family, nitrogen family, oxygen family, halogens, and not really the noble gases because they don't want to bond. But these guys already have like 4, 5, 6, 7 valence electrons. So you've got all these atoms that are going to be more stable by like kind of gaining electrons. That nobody in this region of the periodic table is going to likely lose electrons. If you already have 5, 6, 7 valence electrons, you're not likely to lose those. You want to gain a few. And so here there's this example of fluorine. So you've got fluorine, and he's got 7 valence electrons. So we do a lot of this dot modeling when we think about bonding. It shows us the valence electrons, which are the most important. They're the ones that we want to show having full outer shells. That's stable. And so here's fluorine. He's got his 7 valence electrons, and he wants to bond to another fluorine with 1, 2, 3, 4, 5, 6, 7 valence electrons. Now, it was kind of a while ago where we talked about drawing these dot models to show the valence electrons, and we normally show the dots kind of in pairs just because they would be in pairs in their orbitals. But I think this was like back in the atomic structure unit. We did kind of mention that, if you have, in this case, one oddball, it doesn't matter where you draw it. If you draw that odd electron on the top, on the bottom, on the sides, it really doesn't matter. Now we're going to draw a lot of dot structures in the next week or so. And so eventually you'll get really good at these. And that where you have single dots, that's probably where a bond is going to occur, because that's a spot that I want to fill. I want to get a full outer shell. So the area of interest is wherever there's a single dot. That's where I'm going to want to try to get another dot, right? I want to fill the outer shell with 8 valence electrons. And so if the single dots or the single electrons are the ones that we want to focus on in terms of bonding, it's kind of helpful to put them toward the middle, like face the 2 single dots toward each other, because it's just going to help you see the bond a little bit more clearly. And so it's okay to draw them, like here they're kind of drawn as mirror images. It's totally fine. It doesn't matter technically where you put the single dot, but eventually I think you'll find that the bonding is a little easier if you start putting the single dots toward the center. Because now here's the deal. If I were to say, let's do an ionic bond. Well, ionic bond would involve the transfer of electrons. And so I could take this one electron and maybe transfer it to the other fluorine. So maybe put it right there. But that's not going to fix both atoms. I mean, if I got rid of this guy, fluorine 2, the second fluorine can get a full octet, but the first fluorine is worse. He originally had 7 valence electrons, and now he's down to 6. He's going in the wrong direction. And so here's a situation where we're trying to get these full octets. That's the whole point of bonding. But the ionic transfer, that's not going to work. That's not going to give both atoms a full octet. And so instead, we say, what if they share? If they share by overlapping these orbitals, and often we either show it as like a circle around the 2 electrons, or I kind of like to do this even more. Sometimes people will just like link them up, or they might just like connect the dots. But if we share that pair of electrons in the middle, then counts for both fluorine atoms. They both get an equal share of those 2 electrons in the middle. So each fluorine now can get 8. A shared pair of electrons counts for both atoms. So this covalent bonding is for situations where transferring is not going to help both atoms. Then we look to share. And another giveaway is that these shared electrons will usually happen between two non-metallic atoms, where both atoms are nonmetals. Question 14 then says, what is the relationship between the number of electrons an atom shares in covalent bonds and the number of valence electrons an atom has? Well, I guess mathematically they kind of mention it down here a little bit, but in general, here's the deal. I want to get 8 valence electrons. I want the number of valence electrons plus the number of covalent bonds to equal 8. And so you could write it like that. If I wanted to do it like numerically, valence electrons plus the number of covalent bonds, it should equal 8. I mean, they're kind of showing it down here too. It's just in a little different way, that if I've already got 7 valence electrons, then I need to make one bond so that I can get to 8. So like the halogens are likely to make one covalent bond. Now, when you think about oxygen, and really anything in the oxygen family for that matter, I mean, if I have oxygen, there's 6 valence electrons, and we normally drew them as 1, 2, 3, 4, 5, 6, to kind of show the way that the orbitals would be distributed with their electrons. That anything in the oxygen family with their 6 valence electrons, they'll be organized as 2 pairs and 2 singles. Okay, so if I have 6 valence electrons and I want to get to 8, anything in the oxygen family is likely to make 2 covalent bonds. If I'm in the nitrogen family, the nitrogen family has 5 valence electrons. There'll be 2 pairs and 1, 2, 3 singles. And we'll draw these dots a lot more. We're going to draw a ton of dot structures, in fact. But now I can kind of see if I have 5 valence electrons and I want to get to 8, I'm probably going to make 3 covalent bonds. And the bonds are going to occur where I've got single dots or single electrons. So for example, in oxygen, I'm probably going to want to covalently bond. Oh, let's see. Let's go to this guy. Like this one and this one. In nitrogen, I'm going to want to covalently bond these guys. The bonding will occur wherever I have single dots or single electrons. And so you can kind of think of it in this way, that if I can find the number of valence electrons, the number of valence electrons plus the number of bonds has got to equal 8. We got to get our octets.